Last call. So we're very happy to have Feng Luo from Rutgers University, who will tell us about a dilogarithm identity and finish the conference.
Well, since I'm the last speaker, I think we should thank the organizer, especially Rinat, for organizing the conference. So this is a joint work with Sapil Tang. He is at the National University of Singapore. So let me, this is really about hyperbolic geometries of surfaces. Let me just first give a quick recall of hyperbolic geometry. I'm sure everybody knows it. So a basis of it, we can take it as open upper half plane. And the geodesics inside it are either vertical lines or semicircles perpendicular to the x-axis. You will make a Möbius transformation. The hyperbolic plane could be taken as an open disk, and the geodesics are either the diagonals or semicircles perpendicular to the boundary. And also we know that the isometry group of the hyperbolic space is the orientation preserving one is the same as the Möbius transformation, preserving the upper half space, and that can be identified with the unit tangent bundles. In other words, if I give you any unit tangent vector in the open disk, and you give me another one, I can find the unique isometry of the orientation preserving isometry of the hyperbolic plane taking one to the other one. And so the unit tangent bundle can be identified as a PSL2R. And in particular, PSL2R has this Haar measure, which is bi-invariant, which is left and right invariant. And therefore, in the unit tangent bundle, we have a measure. Sometimes we call this volume or Liouville measure. And it can be written down quite nicely and explicitly. So here is a description. I give you a tangent vector, unit tangent vector V in upper half space, and that determines a geodesic, which is starting from x to y in the x-axis. And then you look at the basis of V to the top of the semicircle and compute the distance. This is oriented distance. And so the distance here now is positive if the basis behind the midpoint is negative. And then the Haar measure has this really nice form dx wedge dy and then wedge du. Okay, so we're going to do some calculations using this measure. And then let me quickly recall the uniformization theorem, which says that I give you any Riemann surface of negative Euler characteristic. It could be non-compact. And then this Riemann surface is biholomorphic to the hyperbolic plane modulo a discrete torsion-free subgroup of the isometry group. And you will take this discrete subgroup acts on the unit tangent bundle, UT. The unit tangent bundle of this hyperbolic surface is then the quotient of the unit tangent bundle of the upper half plane modulo the discrete group, which is really the Lie group marked by the quotient. And what I want to say is that because this measure is bi-invariant, so this measure descends to a measure on the unit tangent bundle of the hyperbolic space. And so we're going to call this the volume of the unit tangent bundle. So this is just a quick recall of hyperbolic geometry. And here comes something really nice. This is Max Cheng in 1998. He proved some really fantastic theorem. Let's take a hyperbolic surface. It's a complete finite volume, and it has cusps. So this is a picture of Max Cheng. So here is a picture. I give you a Riemann surface with cusps, and you put a uniformization metric. And I'm going to fix one cusp. Let's call this cusp C. And now let's take a look at these pans. And so alpha and beta are disjoint simple-closed geodesics, so that alpha, beta, and the cusp form a three-hole sphere. So topologically, it's going to bound this three-hole sphere in the Riemann surface. And then he proved the following amazing identity. So let's look at a set of all such pairs. Let me call this pairs, where one end is this cusp, the other two ends are geodesic alpha and beta, and the absolute value of alpha is the length of the geodesic. You sum over all such pairs, and of this quantity 1 over e plus this length, it's always equal to half. Okay, so this is the Mc-Schien's identity. And so later on, Mitahani and my collaborator Tang and Wang, his collaborator, and Zhang, and generalized this identity to compact hyperbolic surfaces with geodesic boundary. So here is the result. It's a little bit more complicated. I'm going to show you one form of it. And so here D and R are two elementary functions, explicit. So here is a statement. I take a hyperbolic surface with geodesic boundaries beta 1 and beta n. And again, we're going to fix one boundary, like here. So I'm going to pick beta 1 and fix it for all. And now there are two types of three-hole spheres in the surface with the following property. There's one type, it has two boundaries, gamma 1 and gamma 2, and beta 1, they form a three-hole sphere. And all of these are geodesics. And so you take this out and look at the sum of all such three-hole spheres and form a sum where this D is a function of the length of these three geodesics, beta 1, gamma 1, and gamma 2. And there is another type of three-hole spheres where you can take a beta I and then beta 1 and beta I and another geodesic gamma, that will form a three-hole sphere, and you form another elementary functions. This function is independent of the metric, and the statement is that it's always equal to the length of this geodesic. So that's a generalization of it. And so let me show you one form of their identity. This is Mitahani's identity. So suppose the surface has only one boundary, and let's call it the length of the boundaries. This is B is the boundary, and that's Mitahani's identity. Okay, so in this case, there is only one type of three-hole spheres. It's alpha, beta, and B bound the three-hole sphere, and you form the sum. So you will divide this identity by beta, and let beta goes to 0. And so geometrically, we are really producing a cusp, and beta, the length of the beta is shrinking and produce a cusp, and then you recover the Mc-Schien's identity. So here is the picture of Mitahani, and she made really a fantastic use of her identities and produced lots of fantastic results, including computing the Ray-Peterson volumes of moduli spaces and so on. But I'd like to put one more identity before I'm telling you all. So this is a Bridgman 2 years later, produced a different type of identity. Again, we take a hyperbolic surface with geodesic boundary. So this is a compact surface with geodesic boundary. So here's a picture of Bridgman. And he's looking at sort of different style. He's looking at the set of all geodesics goes from boundary to the boundary, and it's perpendicular to the boundary. So alpha, this red curve is a geodesic, goes from the boundary in 90 degrees and ends at a possibly different boundary, but perpendicular to the boundary. And now we compute the length of it, and so here is his identity. It's a fantastic identity. This L is a dilogarithm, the largest dilogarithm. I'm going to tell you, just recall in a minute. So you sum over all orthogeodesics. So these geodesics, let's call these orthogeodesics of A times dilogarithm of 1 over Cauchy. And this quantity, because I just don't divide 8 and 4, is really the volume of the unit tangent bundles, and that's why I like to write it here. So this side is the volume of the unit tangent bundles, and the other side is a dialog. So here is a quick recall of the largest dilogarithm. It takes a value 0 and 0, and its derivative. That's a mistake. The derivative of it. The derivative is equal to this elementary function. Okay, so that's what I want to show you is that this dialog also appears in the closed case. So the question is whether there is something for closed hyperbolic surfaces, and then we will produce one. So for any closed hyperbolic surface of genus G, there is a type of identity on the moduli space. So there are two types of sums. The first type is three-hole spheres in P, where the boundaries are whose boundaries are geodesic. Another type is a one-hole torus, and the boundaries are geodesics. And so there are two functions, f and g, which are dilog, which I'm going to show you in a few minutes. Depends on the length of these of simple geodesics on P's and T, and the total sum is equal to the volume of the unit tangent bundles. So there is a sort of mixing type of identity for the closed case. But I should also say that this formula is explicit, but it's not as nice as the work of the Mizahanis or McShane's. I will show you later.
Could one imagine there also is similar identities with you sum of all pair panels?
That's a great question. We couldn't do it. In fact, I'm going to tell you an open question. There is a potentially better identity, but the quantity involved, we couldn't just compute it. And some physicists may be able to do it, and you will see it. Okay, so this is just one for closed surface, but
this chi this is 2 minus 2g or what?
Yeah. This is the 2 minus 2g, the Euler characteristic of this, and the whole thing is the volume. This type of identity is also true for closed surfaces with geodesic boundaries and cusps. And so there is again such a type of identity which is different from that of McShane, but I'm not going to talk about it. So in other words, for surfaces there could be many other form of McShane identities over there.
Can this also be applied to give some integrals over modular space of curves?
That's a great question. We couldn't do it, and so I will show you. I will show the formula here, even though it's explicit, but it's not so nice at the moment. We couldn't do anything with it yet. Mm-hmm. Yeah, but really, if someone can do some calculation, it would be really great. Okay, so let me just recall some of the notations, and then I'll tell you the basic idea of the proof. Especially I will mention the Bridgman's proof, which is related to ours, and his proof is really beautiful in my view. So let me recall that the sigma is a hyperbolic surface. Ut sigma is unit tangent of the bundle of the hyperbolic surface. It's something like that. And if I give you a unit tangent vector v, it's going to generate a geodesics from V, geodesic rays V from V and V inverse. And so here is a picture. It can produce a forward geodesic, which I'm going to call GV plus going forward, or the backward geodesic coming from minus V, I'm going to call GV minus. And also I'm going to use the volume as a hard measure on the unit tangent bundle. It's the volume normalized is 2 pi times the area of the surface. So the normalized, so that the fiber circle has length 2 pi, and this is going to be the minus 2 pi times Euler. So let me recall the Bridgman's work and his proof. I think it's I really like his argument, and we learned a lot from his construction. So in his case, the surface has boundary. So this is a hyperbolic surface with a geodesic boundary. And now here is the bottom line of all of the proof. We use ergodicity of the geodesic flow. So what does that imply is that for almost every unit tangent vector, this is almost every with respect to the hard measure, both the forward and the backward geodesics is going to end it at the boundary. So here is a picture. So if you generically choose a unit tangent vector on the hyperbolic surface and look at the forward geodesics, those who's going to stay always inside has measure 0, because those geodesics stay inside is invariant under the geodesic flow, and the ergodicity will tell you has measure 0. So for generic choice of unit tangent vectors, the forward and backward geodesics is going to end it at the boundaries. Okay, so in other words, this is going to generate a geodesic arc from the boundary to the boundary. And now here is a very simple topological fact. that if I have a geodesic arc from the boundary of a surface to the boundary of a surface, it's always going to be homotopic to a unique orthogeodesic. So it's a very simple topological argument. Or just I give you this blue geodesics just within the homotopy class, where the homotopy leaves the endpoints in the boundary. So it's allowed to move in the boundary but cannot leave it. You just look at the shortest geodesic within the homotopy class, and that's going to be also geodesic because the shortest implies it has to intersect the boundary in 90 degrees. So we have a decomposition. The unit tangent bundle now is decomposed as a measure zero set. This is a non-generic one. Disjoint union of B alpha, where alpha is also geodesic. So if you take orthogeodesic, and I'm going to look at the set of all unit tangent vectors where the geodesic generated by it is homotopic to alpha. So here is a picture. So I fix now this alpha, and I look at these unit tangent vector V, and look at the geodesic generated by it. And so this is GV, is this blue curve, and it's homotopic to alpha. So this is a sort of a decomposition. This is always the standard way of doing it. We decompose some well-known space in this way, and then we try to compute the volumes. So the Bridgman's identity is now just take the volume of this, and we have that. And the question is, of course, can you actually compute this volume? Is this volume computable? And here is his argument. It's this really beautiful argument I like to show you. So let me repeat. The question is, I give you a geodesic from the boundary to the boundary. It's orthogeodesic. And I look at the set of all unit tangent vectors in the surface, so that the geodesic generated by this unit tangent vector is homotopic to alpha. And I would like to know what is the volume of that. So here is a picture. Let's take alpha to be this red curve from geodesic A to geodesic B. And I'm really looking at the set of all these blue geodesics, blue geodesics from A to B, and really look at the unit tangent vectors of all of these geodesics. And you go to the universal cover. So first, let's lift this alpha to the universal cover. It's going to be a geodesic arc. And then we're going to lift the geodesic A and B to the universal cover. So it will be A theta and B theta. Both are perpendicular to the alpha. Okay. Now, because this blue geodesic, this blue geodesic is homotopic to alpha, and we can use the homotopy lifting of the covering space. And so this blue curve is going to be lifted to a geodesic, go from A theta to B theta. So that's going to be the lifted curve. And by a very simple observation, now the set of B alpha is really the set of all geodesics from A theta to B theta. And you look at the set of all unit tangent of those. So let me put it another way. We are looking at, in the universal cover, the unit tangent vector in the upper half planes. So the forward geodesic is going to intersect A theta, B theta, and backward geodesic is also intersecting it. And the question is, can we compute that? And that's a much simpler question. And I'm going to show you by the end. It's a very simple integrals, and he was able to integrate it and get to this formula that it's coming from the dilogarithm of the length. And so this set, the volume of that depends only on the distance between the two geodesics, which is the length of alpha. So let me now go back to our theorems and to see how we proved it. It's kind of similar. Let me just you take a closed hyperbolic surface, you look at the set of all embedded geodesic one-hole torus and three-hole spheres, and we can get some kind of a identity like that. And the basic idea is the same. Namely, we like to decompose the unit tangent bundle according to these subsurfaces, and we hope we can compute these terms involved. So here is a strategy. I give you a hyperbolic surface. I like to decompose the unit tangent bundle according to one-hole torus and three-hole sphere geodesic subsurfaces. And let's assume the surface has no boundary. Again, use the ergodicity of the geodesic flow. Now, in this case, it will say the forward geodesics and backward geodesics is going to intersect itself as time goes to infinity. So this is sort of the counterpart of Bridgman's argument. If you generically choose a unit tangent vector in a hyperbolic surface, and then it's going to intersect itself. The point is, if it remains simple, then the set of all such simple guys is going to be invariant under geodesic flow, and therefore has mu equals 0. Okay, so the next thing is sort of our key construction. I take a generic unit tangent vector V, and I'm going to grow the geodesic coming out of it. So I'm going to grow both the forward and backward geodesic and at the equal speed. Okay, so as time so the forward and backward move at an equal speed, and so let it grow, and then at certain stage one of them is going to intersect according to the ergodicity. So at certain stage, so say the forward geodesic is intersect either itself or the backward geodesic. If that happens, we stop. So this forward geodesic, when it intersect something, you just let it stop grow, and then you let the backward geodesic grow, and eventually it's going to intersect again. Okay, so this is a way to associate a graph to a generic unit tangent vector. And I like to emphasize this is a key construction, so let me show the movie one more time. You just keep grow, and then you stop. Okay, so that's it. And now let's define a graph generated by this vector GV. This is a graph which is always, by the construction, homotopic to a wedge of two circles. In other words, Euler characteristic is always -1, and that's where these two surfaces comes in. We have two surfaces here, three-hole spheres and one-hole torus, and these are the only surfaces whose Euler characteristic are -1. Okay, so it's coming from this construction. So let me now prove a lemma which says that for this graph, there exists a unique three-hole spheres or one-hole torus geodesic subsurface in the surface which contains this graph. In fact, they are essentially homotopic to it. So the picture is something like this. It could be this is a graph and this is a subsurface. And so let me show you how the proof goes. The proof is quite pictorial. So we just take this surface and cut along this graph, and we will get a convex surface. The convexity is the key. So we will get a surface with convex boundary. So here is how. You take this graph. This is a geodesic segment with some vertices, and we cut it along the geodesic, and we get a surface with boundary. And there could be some corners because you cut along the geodesic, and there are some corners here. And so let's take a look at the corners. This corner here comes from the corner there. So these corners are coming from here. The key observation is that by the construction, these corners all have angle less than or equal to pi. So, okay, so this is the key observation. So the surface we get in this construction, if you cut it open, it's always a convex surface. And if we have a convex surface, we can do pretty much all of the geometries like in complete surfaces. For instance, here we have a convex boundary, and the boundary is going to be homotopic to a unique geodesic. Because of the convexity, the unique geodesic homotopic to the boundary is going to be inside. So here is the picture. You take the geodesic homotopy to the boundary, convexity says the geodesic is still stay inside, and there is annulus between the two because the boundary is a simple one. And just to glue them back. So glue them back, and that's the surface piece. So this is how we produce this geodesic surface P and T, which are essentially homotopic to the graph. And so by this construction, we can now decompose the unit tangent bundle as a set of measure 0 due to ergodicities according, and then it's a disjoint unions of P's and T's, where WP, it's like in Bridgman's construction, those unit tangent vectors whose graph is homotopic to P. In fact, it's inside P, and define the T is the same way. And we get identity. So this is the sort of the basis of the identity that we have. The question is whether we can compute this now. Okay. Before it turns out we can do it. It's involving the dilogarithms, the length of the boundaries. But before I go to the actual calculations, I'd like to ask a question. There is, in fact, even simpler decomposition of the unit tangent bundles, which we don't know how to compute. And if one can compute it, the result could be even better. So here is the open question. I start with a closed hyperbolic surface, and I take a generic unit tangent vector, and I just look at the forward geodesic. Let's forget about the backward geodesic. It's not simple according to the ergodicity. So we're going to get this picture. It's going to be moving forward, and it's going to self-intersect. And if it self-intersect for the first time, you're going to produce a simple loop here. And this loop has only one corner, and so it's homotopically non-trivial, and it's homotopic to a simple closed geodesic gamma. And that produces the decomposition of the unit tangent. So we can now index, we can decompose the unit tangent bundle according to measure 0, and then index by a simple closed curve on the surface. And just like the same construction, and the question is, can we compute the volume of this? And we don't know how to do it. Okay, so if it's true, it will be kind of nice because this side is just the set of all simple closed geodesics. Okay, so so let me now tell you the form of the function that we get. I'm going to just show you the case of a three-hole sphere. So I suppose I have a three-hole sphere hyperbolic surface with geodesic boundary, and L1, L2, L3s are L1 are the lengths of the geodesic, and we can also determine the geodesic from the boundary to the boundary. So Mi is going to be the geodesic, shortest the geodesic from Lj to Lk. And let's let xi to be e to the minus li and yi to be mi. Then this volume is given by this formula. Okay, so L is I, so 1 minus xi's and so on. And this, I like to say that three terms here appears in the pentagon relation for dilogarithms. We cannot simplify this any further. So the first three terms here are exactly the one appeared in the pentagon relation for dilog. And this is the term which we don't know how to do anything. And so there is a similar identity for one-hole torus. I don't want to show it to you, but if you're interested, I can. Okay, so that's a result, and as you see, this is not as nice as the machines, but it's still. Okay, so let me quickly tell you how to compute this volume. This is now just focused on a single three-hole sphere hyperbolic surface, and we're looking at the unit tangent vectors inside it. It's going to generate a graph which is homotopic to it. And so can we compute the volume of it? That's a picture. Okay, so and first, if we look at the volume of the unit tangent bundle over the whole space, this is going to be minus. It's 4 pi squared by by Gauss-Bonnet. So we really compute the complement of W. So what is the volume of the complement of this set? And that's, so let's take a look at how, if I have a V which is in the complement of this set, what is this? What is this set? It says that if you look at the forward and backward geodesic, it could be just simple. Okay, before it self-intersects, it's already bumped into the boundary. But the first case is from one boundary to a different boundary. The second, it could be from the one boundary back to itself, but it's simple. The essential case is this. Okay, so it self-intersects before it bumps into the boundary, and we call that a lasso. And the lasso case, it turns out there are two situations. It's a little bit technical, but so this is a true lasso, meaning the short, also geodesic homotopic to it self-intersect. This is a fake lasso, where the also geodesic homotopic to it is simple. And what Bridgman did, really, so Bridgman really take care of these three cases. Okay, so this is already done. So what we actually computing is this true lasso. It's a little bit more complicated situation. So let me tell you this details a little bit. A lasso is a geodesic segment from 0T to the 3-hole sphere. It starts from the boundary, and before the final time, it's simple, and then at time t, it's bumping to self. Okay, so but there is also a midpoint. So there is a lasso here, and you look at the midpoint of the lasso, and that's very important for computations. I'm going to call M alpha at time alpha is at the midpoint. You look at the vectors, unit tangent vectors before the midpoint. This is another picture. These unit tangent vectors are the vector which we call is going to generate this lasso. If you pass the midpoint, it's not going to generate a lasso. In fact, by the construction, if you have a unit tangent vector here, and you let forward and backward geodesic grow, it's going to pass this point before it's reaching here. So it's going to generate a different lasso. So that's why we look at those unit tangent vector before the midpoint. So the question is, the previous question is, can we compute all unit tangent vectors in a surface so that it generates a lasso? Okay, that's another translation of the problem. So here is another simple pictorial lemma, which is really helpful for us. Suppose I have a lasso. This is a blue curve going from and the lasso by understanding this gamma. And the proof is also quite simple. It's all this is sort of Thursday style geometry. So we draw pictures and do some cutting and paste. So we cut the hyperbolic surface open along the lasso. And by all of these constructions, the surface you get is always going to be convex because this is angle pi and something less than pi. So we get a convex surface. This is just part of it. I look at the other. So you cut it open, has two component. I look at the other component, and this point P breaks into two points P and P prime, and you just look at in this convex surface the shortest path from P to P prime, and that's being the shortest implies it's going to be simple. And also, because the boundary is convex, this curve gamma, this red curve, is not going to intersect alpha except as the initial point. So that's. So let me just rephrase it. I have a lasso. So I like to understand the set of all unit tangent to the lasso before the midpoint. And by the previous lemma, I can produce some kind of bounding gamma of it. This gamma is a simple geodesic loop disjoint from alpha. And then let's take a look at, you cut it open along gamma, and you get a annulus now. This is the annulus with one geodesic boundary, and the other boundary is convex. And this is the annulus which contains the lasso. So lasso starts from the cone point and stay inside. So by the end of the day, it reduces to understand geodesic segment in this convex annulus with one cone point, and that's a much simpler problem to work at. So here is a little bit more the technical details. We look at a set of all unit tangent vectors generating. Let's fix a lasso alpha from a point P in L2, and is homotopic to a boundary L1. So we fix sort of a homotopy type, and also I'm going to fix this space point. And we like to see what are the set of all possible unit tangent vectors in this setting. By the previous construction, it reduces to this convex annulus bounded by this gamma and L1. And if you look at the universal cover of that, it's going to be, so I'm really looking at this annulus here, and the universal cover is going to be this whole region. Okay. And the lasso here lifts to this picture. So you look at the lifting of it. Lasso starts from one of these cone points and goes out. And the technical observation is that we're only interested in those unit tangent vectors, which is whose base point is before the midpoint, and the midpoint becomes a tangent point. So let me summarize what this analysis tells you. It's really this. This is very similar to the Bridgman's analysis. This set in the surface is complicated. You could go to the universal cover and identify it with a subset of the universal cover. And so in this, by the previous analysis, it reduces to this picture. This is now getting explicit. So we are looking at, I have CD is the lifting of L2, the y-axis is the lifting of L1, and the distance here is the shortest. The distance, this is another lifting of L2. So what I'm looking at are the set of all geodesics. One base point is between 0 and A, and the other endpoint is between C and D. So that the geodesics from X to Y, we are only calculating the unit tangent from the intersection point to the tangent point of the geodesic to the geodesic ray from 0. Okay, so that's the final sort of analysis of the set, and plus some computation by Bridgman. So let me tell you. So this is the bottom line. It turns out we can actually compute it. So here is this proposition has nothing to do with the previous analysis. It's really sort of calculus. So the statement is I give you C and D, which is bigger than 1, C less than D, and I'm looking at a set of all geodesics from Y, which is between C and D, and X is between 0 and 1. You look at the unit tangent from P to the midpoint, and that can be written down by the hard measure I wrote down at the very beginning. This is the integral. Okay, so this is the actual volume of it, and by a little more calculation, it turns out to be the dialog. So let me finish this. So this is what Bridgman actually calculated. In his case, he fixed two geodesics. One is the y-axis, and the other one from S to 0. And he's looking at the set of all geodesics crossing y-axis and S0 geodesics. Really, you look at the set of all unit tangent vectors from this portion. and he was able to analyze that. It turns out this is a simpler case than us, and that's what he get, and that's what we get. So it's interesting that all of these intervals, it turns out to be related to the dialogue. So I think I'll stop here. Thank you.
Any questions?
Yes.
Did you try to look at sort of the pressure technology for ergodic flows?
No, not yet. Yeah.
Because there is this Lifshitz-Höller classes whose integration over the whole space can be evaluated by summing over all the special orbits. And so I'm simply wondering whether by varying the cohomology class to measure various different aspects about the closed geodesics, you could actually somehow generate many of these identities.
Yes, that's in fact a good point. I think it's not just one identity. There are lots of interesting identities out there to be discovered. Yes, I agree.
Yeah.
Yes.
So focus on the periodic orbits as opposed to computing all of these areas that you are, or volumes that you are doing at the moment.
Right. Yeah.
So I think pressure technology could
Yes,
really
yes.
be applied here with great.
Yes, that's a good point. Yeah, but I don't know too much about this. Yes.
So does there exist some other identities involving other topologies than chi equals -1?
Not I know of at the moment. Not I know. It's a good question too. Yeah.
You know, I'm referring to the Bowen theorem that says that the measured average all over the space is the same as the sum of the delta functions on the closed orbits. Like Thurston's formula for the pressure metric and cyclone space.
No more questions? Let's thank the speaker.